Yes, so now we have a few minutes for questions. We had a lot of very interesting questions already during the webinar and answered some of them, but some we couldn't answer, and we will do that now. So I've noted down a couple of questions. One question that was very interesting was that the user asked whether the actual temperature jump is always a real discontinuity, or if it can also be just a transition to a smooth slope. And actually, both cases are possible. Really, in the end, depends on the nature of the interface. So a very a true discontinuity you would only have if you really have an atomically very sharp interface. But you always have some kind of transition region where you go into some kind of amorphous state or amorphous structure in between the two crystals, and there you would, in fact, expect a very steep slope instead of a true discontinuity. And in some cases, for example, if you have a larger amorphous region in between the two crystal regions, for example, or if you have the interface from crystal to an amorphous, it can be that you don't have a jump at all, but that the profile is actually continuous. It just changes the slope when you change the region. So that's, to answer that, what kind of discontinuity or change of slope you see depends very much on the actual interface and especially how well the contact between the two materials is. If you have a lot of covalent bonds, then you might have a good conductance along the interface. However, if you have a lot of dangling bonds, so to say, then the conductance would be reduced and the jump would be more pronounced. Also, it depends on how well the two sides of the interface can conduct thermal energy. So if both sides have a very good conductance, like we have in the case of perfect crystal, the heat that would come across the interface would immediately be transported away. However, if on the other side you have a poor thermal conductance, then the heat that would be transmitted through the interface could not be transported away so efficiently. So you would rather have a continuous transition to a much steeper slope on the other side. So that really depends on what kind of systems you have. Another question that we have is if it is possible to use these atomistic simulation techniques for example, solid-liquid interface to calculate the thermal conductance across solid-liquid interfaces. And here, this is very well possible using the non-equilibrium molecular dynamics simulation. Here you can actually set up a system, for example, having two surfaces and having a region of a liquid material in between two surfaces and running a non-equilibrium molecular dynamics simulation of that. And that should be very well possible to run such also the thermal conductance across solid-liquid interfaces. There are, I just checked it while Casper was doing the hands-on, there are a couple of papers who actually show such simulations as thermal transport simulation across solid-liquid interface. So if you search the literature, there's a couple of examples available already. However, you cannot use the non-equilibrium Green's functions technique for this kind of simulation, because basically the transport mechanism would not be harmonic propagating phonons in the liquid part. So the harmonic approximation would not work in the liquid part. So here you can only use the non-equilibrium molecular dynamics technique. Another question that we had that was already partially answered by Casper is, what about metals? What do we have to take care of when we calculate the thermal conductance of metals? And here in metals, since you have also conducting electrons, you have a quite significant contribution to the thermal transport and thermal conductance by the electrons, and that is of course not taken into account in the techniques that we've talked about today. But as Casper already said, you could run an electronic transmission calculation, basically the equivalent of the phonon transmission, just considering the electrons instead. That is easily doable in VNL. And then you could use the thermoelectric coefficients plugin to calculate the electronic contribution to the thermal conductance. However, here you also have to be a bit careful. If you have a perfect system, you only consider a ballistic transfer. So if you have a perfect system without any disorder, you might actually overestimate the thermal conductance here due to the same reasons that you overestimate the thermal conductance due to phonons in a perfect system. Were there more questions, Casper, coming in right now that we should take?
So did you go through the Q points of so we said only one Q point in the phonon transmission spectrum.
Yes.
So this we mentioned that you may want to use more Q points in the normal simulation.
Yeah, in the normal simulations, you basically this is the way you take into account the periodicity, the lateral periodicity at least of the system. So you can basically just simulate a system which is just a unit cell wide and use a lot of Q points in order to calculate, in order to take into account the periodicity. So you don't have to have a system that is so large that it can accommodate all the phonon modes explicitly, but you can basically just increase the number of Q points just as you would in a calculation of a phonon band structure, where you also just calculate the phonon band structure of a unit cell, but essentially take into account the periodicity by using Q points, and that's basically the same mechanism here. On the other hand, as I said, in molecular dynamics, you don't have this possibility, so here you basically have to increase the size of the cell in order to accommodate or to take into account larger wavelength. Otherwise, you have a very, or the smaller your cell, the, let's say, the coarser the resolution of your Q points is.
So also when you do the non-equilibrium molecular dynamics, you should increase the size of the system until it's converged.
Yeah, you should. Well. In interface thermal conductance, you should. It is not, the finite size effects are not so severe, but you should make sure that the values do not change dramatically when you increase the size of your cell. For thermal conductance simulation, that is only one of the problems. The other problem is the phonon mean-free path. So you basically have to extrapolate the length, so basically the distance between the two reservoirs, and calculate for each length the thermal conductivity and extrapolate the thermal conductivity to infinite wavelengths. Another point that we had is why it is necessary to, so can we go to the questions to check if there's anything we need to answer?
Yeah.
Another point that we had is why do we set up 3 equilibration or 3 MD simulations before? Why can we not directly start with the non-equilibrium molecular dynamics simulation? And here, basically, when you start introducing the thermal current in your molecular dynamics simulation, you must already have an equilibrated system, because at the moment where you start your non-equilibrium molecular dynamics simulation, you switch off the thermostat. You just swap the momentum, but you don't control the temperature anymore. So when you start the simulation, you want to actually already have everything at equilibrium. Otherwise, you cannot make any step, or it's difficult to control the average temperature of the system at which you want to calculate your thermal conductivity. That means this 600 Kelvin that we set here. So we first need to equilibrate the system at normally also at constant pressure, but at least at constant temperature. And only when you have a system which is at equilibrium in the constant pressure, you can start the non-equilibrium molecular dynamics simulation. That means we can start swapping the momenta and thereby transferring thermal energy from one system to the other. That's the reason of those initial equilibration simulations. Another question is, do you plan to use anharmonic effects in future releases? And So as I said, in molecular dynamics, we already have anharmonic effects fully included. Everything, so we don't make any harmonic approximation here. Everything is fully included. We have some plans to, or we're thinking about if we should calculate also anharmonic force constants, so that you could from that calculate the phonon lifetimes and include it in the Boltzmann transport equation. But this is only plans for, not for the upcoming release, but maybe for the release that's coming after that. We have not finally decided about that, but it's definitely something we consider important and we think about implementing. What more questions did we have? There was one question was actually that in the literature people use 3D periodic boundary conditions for the non-equilibrium molecular dynamics simulation. So that means they do not use the slab geometry with the two surfaces and the vacuum in between, but they use a fully periodic system. And that is also possible, but basically then you have thermal current in both directions. So also across the periodic boundary conditions, you basically have to use a system which is twice as large, and your temperature profile would be basically mirrored. So you would have one slope going to the left and one slope going to the right, and the results should be the same. This 3D periodic geometry is more a thing that people used some years ago. Now, when going through the literature, it seems that the trend is more that people basically use the slab geometry, because it's simply the results are actually the same, and it's just a lot more efficient. But both geometries are possible.
So I'm just showing here on the screen how you could do that. So when you have the device interface geometry that we had originally, it's what I'm highlighting here. You can repeat this along the C direction, and then this part here you should then mirror such that the 110 will see itself the 110 also here, so that the heat will flow from the center of them towards the sides. So this can also be generated, of course, this kind of configuration with the builder. You can build this very easily also here. But like Julian said, it's just it's not necessary to make such a big structure to do these studies.
Yes, I think that was all the questions for now. Also, our time starts running out, so already 10 o'clock here in Copenhagen.
Yep.
We would like to thank you all very much for attending the webinar. We had a lot of fun. We were excited that so many of you came, and we hope you learned a bit. You learned something new that you didn't know before. We hope you enjoyed the hands-on session, and we are planning more webinars in the MD series. We have not scheduled the webinar yet, but we will announce it on our website as soon as we have scheduled the next webinar. So check out our website, quantumwise.com, to be sure that you don't miss the next webinar. And yeah, thanks again for watching. Have a good evening and have a good day wherever you are in the world. Yeah, that's everything from us for today.
The very last thing I just wanted to mention is, of course, if you had any questions or you get questions later on, we have the tutorials part of the website, which has an extensive list of tutorials on all sorts of topics, of course also molecular dynamics. We have a forum which is very active, where you can expect to get a reply within just a few days. And then of course our website, where new webinars will be announced. So yeah, like Julian said, thank you very much for attending, and see you next time.
Yes, see you next time. Goodbye.